Good morning, children. In today's video, we will be discussing some important questions from group 13 and 14. It's a part of P block elements, class 11. Okay, so we begin with reason questions. Give reason. Give reason for the following. And in inorganic chemistry, these type of questions are very, very important. Okay, so the first case is the atomic radius of gallium is lesser than aluminium. Normally, what you expect is group 13 elements. It's a member of group 13. You have boron, aluminium, gallium, indium, thallium. So what you expect is down the group, the size should be increasing. Size is increasing throughout, but the only exception is aluminium and gallium. Gallium is found to be slightly smaller in size than aluminium. So what reason you will write? The atomic number of aluminium is 13 and the atomic number of gallium is 31. So this is the element which is coming after first transition series. That is from 21 to 30. This is the first transition series. So this is the first element after the first transition series in which the last electron was entering into d orbital. Okay, and the d orbitals are larger in size. They are larger in size. They have large size, you can say. Okay, and their electrons, these orbitals are not able to provide effective shielding. You can say in a way the size decreases because of the poor shielding provided by d orbitals. Okay, the electrons of the d orbital provide poor shielding, due to which the size of the gallium is slightly smaller than the aluminium. Okay, so in a way we can say the nuclear charge in gallium is much more than aluminium. The effective nuclear charge. The nuclear charge in gallium is more than aluminium. I hope the points are clear. There are 2 points you will write down. Firstly, you will write down in gallium d orbital is being filled and the d orbital is comparatively larger in size. Therefore, the intervening electrons do not shield the nucleus effectively. The intervening electrons do not shield the nucleus effectively. That means we can say they have poor shielding. Therefore, the nuclear charge will be more in gallium. Right. Next, it says the first ionization enthalpy of group 13 elements is lower than group 2 elements. This you can explain taking example of second period 2 elements, that is say beryllium and boron. Beryllium configuration, valence shell configuration is 2s2 and boron is 2s2 2p1. So you can explain on the basis of the configuration that in beryllium the last electron, that means the first ionization enthalpy, is to be removed from s orbital, which is completely filled. S orbital which is completely filled. So because of completely filled configuration, it is difficult to remove electron from it. Wherein in boron, the last electron is to be removed from p orbital, which is having 1 electron in p. So it can lose this electron readily so as to achieve stable configuration of S2. Second reason you can give is the penetration effect. You can give the penetration power. Penetration power of s orbital is greater than the p orbital. So because in this the electron is to be removed from s orbital, more energy will be required to remove electron. Here the electron is to be removed from p orbital, it can easily lose the electron. The next question says electronegativity decreases from boron to aluminium. From boron to aluminium, electronegativity decreases and then increases down the group. Now to answer that, what you will do is you have to talk about size. Just now we saw from boron to aluminium the size increases. Size increases, that means from boron to aluminium, when the size increases, the electronegativity will decrease. Till here it is fine, right? Because when the size increases, the tendency to pull electron toward itself decreases, so electronegativity will decrease. So from boron to aluminium, the electronegativity is decreasing. But thereafter what we find? Gallium, size is decreasing, but for gallium, beyond that, size is increasing. But still you find that the electronegativity is increasing beyond that. The reason for that, you will write down that is the effective nuclear charge increases. Down the group, effective nuclear charge increases. The reason for that will be due to poor shielding of inner D and F electrons. Because of poor shielding of inner D and F electrons. As a result, the force of attraction of the nucleus for the electron will increase. Force of the attraction will increase, thereby electronegativity will increase from aluminium to thallium. Right? Next, it says density increases down the group. To explain density, you will be focusing on density is mass by volume. Down the group, mass increases, volume also increases. Volume means the size increases. So whichever increases more, it is observed that the increase in atomic mass is much more than the increase in the volume. So we can say the atomic mass of the element outweighs the effect of the increased atomic size, due to which the density increases down the group. Clear? Next, it says the stability of the +3 oxidation state decreases and that of the +1 oxidation state progressively increases down the group. To explain the oxidation state, you focus upon their configuration. The valence shell configuration of group 13 elements is Ns2Np1. That means the common oxidation state for group 13 element is +3. Right? So we are saying down the group, the +3 oxidation state tendency decreases. +1 is increasing. Why? Because the last elements, they exhibit inert pair effect. Inert pair effect, due to which the pair of the s electron doesn't get unpaired. It doesn't participate in the bond formation. So only +1 oxidation state is shown. And particularly thallium. Thallium is the element which shows only one oxidation state, that is +1. Wherein gallium and indium, they show both +1 and +3. So overall we can say the stability of +1 is increasing and +3 is decreasing. The same reason can be given here also. Thallium cannot exhibit +3 oxidation state because of inert pair effect. Inert pair effect you can write down. It is lying in 6th period. So configuration is 6s to 6p1. Only this can participate, not this one. 6x. 6s because of inert pair. It is one of the consequence of the lanthanide contraction. The next question says BCl3 on hydrolysis forms BOH, taken for here -1 charge, wherein aluminium chloride on hydrolysis can form this. You can clearly see the compound that is formed by boron has the maximum coordination number of 4, whereas that formed by aluminium has the coordination number 6. So this can be related to the configuration. Boron configuration is 2s2 2p1, wherein you are having only 3 p orbitals and 1 2s orbital. That means only 4 orbitals are available. So it cannot exhibit coordination number more than 4 due to absence of d orbital. Due to absence of d orbital. So it is having only 3 orbitals which are involved, and hence the hybridization will be sp3 hybridization. Okay, wherein you find here the coordination number can be 6. The d orbital also can participate. Aluminium configuration is 3s2 3p1, but 3d is also there, which is vacant, which is not having any electron, but it is there, so the electron can be excited in that. So the hybridization, what it can exhibit is sp3d2, which is having octahedral. This is tetrahedral. So it is having d orbital, wherein boron doesn't have d orbital. So due to the absence of d orbital, it cannot have a coordination number more than 4. Aluminium can have 6. All other elements can have 6. Lewis acid character decreases down the group. That means the halogen is same, the central element is changing. Lewis acid is that which is electron pair acceptor. Electron pair acceptor. If the central element is changing, you will have to check for the electronegativity of the central atom. More the electronegativity of the central atom, more will be the Lewis acid character. More the electronegativity, more will be the Lewis acid character with reference to the central atom we are saying. Electronegativity of the central atom, if it is more will be the Lewis acid character, because if it is smaller in size, electronegativity will be more tendency it will have to take electron pairs. Therefore, it will be a better Lewis acid. The next says both boron and aluminium halides are Lewis acids, but only aluminium halides exist as dimers, wherein boron halides only exist as monomers. For this, you can write boron is small in size. It is having very small size, due to which it cannot accommodate large sized halogens around it. Therefore, dimer is not possible for it. Okay, so what you can have for boron halide, it is a Lewis acid only. It is just taking electrons, like you can have say BF3, it is taking pair of electron from ammonia. So it is only existing as a monomer. If you see the structure, boron fluoride is like this. It is just trigonal planar. If you are writing for aluminium chloride structure will be like this. 2 aluminiums you will mark, and then chlorine atoms will be there here like this, and it will form a dimer like this. So where chlorine is giving electron pairs. The lone pair of the chlorine and the unshared electron pairs are giving electron to the central atom. It can exist as a dimer. Boron cannot, because it cannot accommodate large sized halogens around it. Concentrated nitric acid is transported in aluminium containers. So for that we can write aluminium has an important property of forming a protective oxide layer coating. It forms a layer of the protective oxide around it, which doesn't allow aluminium to react beyond certain extent. It will form Al2O3. That Al2O3 will cover the aluminium container. So beyond that, concentrated nitric acid cannot react with it. So since concentrated nitric acid is a good oxidizing agent, it's a good oxidizing agent. It can oxidize aluminium to aluminium oxide, and once that coating around aluminium is formed, further reaction of aluminium with nitric acid can be stopped. Right? Moving on to the next question. On moving down the group, the basic character of the oxides increases. That means we are mainly talking about group 13 elements. The basic nature increases down the group. Right? The basic nature increases down the group. The answer to that is metallic nature increases. Metals form basic oxides. Non-metals form acidic oxide. And in group 13 elements, mainly in P block, you will find all variety. Like if you specify here, you have boron, B2O3, it is acidic oxide. It is acidic oxide. The next one, Al2O3, Ga2O3, gallium oxide. These two are amphoteric oxide. These two are amphoteric oxide, right? Then you have indium, In2O3 and Tl2O. These are basic. You will have the last one as most basic, but of course both are basic, right? Aluminium has amphoteric behavior. Now, to explain the amphoteric behavior of aluminium, we can write its reaction with acid as well as base. This is actually justify type of question. Justify with the reaction that aluminium is amphoteric in nature. So you can write reaction of aluminium with HCl, wherein it is forming the salt, plus it liberates hydrogen gas, right? So in the same way, you can also write down the reaction of aluminium with the base. With base NaOH, there is water also. So when you form the product, it is NaAl, OH taken 4 times. It's a complex compound form plus hydrogen gas. Okay, so I have not balanced the equation. The balancing you can do on your own. There is a line here. I hope that part is clear. Now, the next question says Lewis acid character decreases in the following order. If we are talking about only boron halides, boron, iodide, fluoride, chloride, bromide and so on. So it is found that boron fluoride is least acidic in nature. The answer to that question is boron. If I talk about fluoride, of course the shape for all is the same, trigonal planar. But since fluorine is smaller in size, each fluorine is having 3 pairs of electron. It is having 3 pairs of electron on it, each fluorine, right? So because of small size of fluorine, what happens is these electrons are given, 7 electrons are there on each. Yes, that you can mark. So because the size of fluorine is small, there is a possibility of back bonding. In BF3, there is a possibility of back bonding, due to which the lone pair of the electron, or you can say the non-bonding electron pairs on fluorine, can be donated to the central atom. So its Lewis acid character is slightly reduced due to back bonding, which is not possible in the other halogens because they are larger in size. So when they are larger in size, the back bonding will not be there. They will not be able to give electrons to them. Okay, so this type of bonding we can say as p-pi back bonding. P-pi, because the p electrons from here are given to the p of that. So p-pi back bonding is possible in BF3 but not in other elements, right? The next question says boron exhibits abnormal behavior. Why boron is abnormal, they want to ask. What is the reason for it? So same set of reasons you have. Small size, ionization enthalpy is high. Of course, because of small size, ionization enthalpy has to be high. The next point you can write is absence of d orbital. Absence of d orbital, due to which boron is abnormal. What all properties boron is abnormal? So actually speaking, you can learn all based upon the multiple choice or 1 mark question what is asked, but at least 4 main properties you can remember in which boron is acting as abnormal. So you can write down first one as it forms covalent. It forms covalent compounds. Then you can have boron oxides. Boron oxides are acidic in nature, whereas all other are amphoteric, or you can say they are acting as basic oxides. It is mainly acidic, right? Then further you can write it cannot have coordination number more than 4. The maximum coordination number what it can form is 4. Then you can also write that boron halides exist as monomers. They exist as monomers. They cannot be more than that because of small size. It cannot be surrounded by more number of large size halogens. Boron is unable to form BF6 minus. The answer to this is also based upon coordination number. The maximum coordination number is 4. So absence of d orbital. Absence of d orbital, due to which it cannot exceed its covalency to 6. So there can be different types of questions asked, wherein the answer might be same, but you should be exposed to all type of questions. The next question says that white fumes appear around the bottle of anhydrous aluminium chloride, because anhydrous aluminium chloride, when it fume, some moisture is there with it, around it some moisture is there. Originally it is anhydrous, but white fumes will appear only when it is exposed to moisture. So it will combine with water to which it is exposed. So it will result in the formation of aluminium hydroxide, and HCl fumes will be formed. HCl fumes will be formed. So fumes are seen, that is why it appears as if white fumes are coming around the bottle. Carbon has unique ability to form p-pi multiple bond, whereas other elements of carbon-14 cannot. So answer to this is carbon has small size. Small size. Because of small size of carbon, it has the tendency to overlap laterally. Lateral overlapping will be effective. Lateral overlapping is effective in case of carbon. Lateral overlapping is effective. Whereas if you say the other elements, say you have germanium, you have tin, lead, they are large size. So when they are large size, the p orbital of one and the p orbital of oxygen atom, they'll be far away. Or with themselves also, if they are forming, say if it is tin and tin, p orbital of one tin, p orbital of another tin, they'll be far away because they are large size. So the lateral overlapping is ineffective in them. In carbon, due to small size, lateral overlapping is effective. And in the other elements, large size, lateral overlapping becomes ineffective in them. Next says the order of catenation is like this. Why the catenation order is in this manner? Catenation tendency is dependent upon size. It is said that catenation tendency is inversely proportional to size. Smaller the size, more the catenation. So if you keep this in mind, carbon is smallest in size, so this is having the maximum catenation tendency. And down the group, the size decreases. So in a way, carbon-carbon bond strength is maximum. You can also say if the size is small, the bond strength will be more. More the bond strength, more will be the catenation tendency. So carbon-carbon bond strength is maximum as it is smaller in size. So this will have the maximum catenation tendency. Okay, down the group, size of the atom increases, bond length increases, bond strength decreases, so they will not have more catenation. Right? In catenation, one very important thing, you have to talk about the single bond between them, not double bond. If you are talking about a double bond, then it is not catenation. Okay? Lead does not exhibit catenation because of large size. It has large size. Moreover, it is metal. In metals, there is no catenation. In fact, it is seen that lead bond strength is the least, that is 800 kilojoules per mole, wherein in all others it is 200, 300 range. So this is the least, wherein in carbon, the bond strength is maximum. It is nearly 348 kilojoules per mole. So that is why the carbon has the maximum catenation. Small size, more electronegativity, more bond strength, less bond length. These are all the reasons why carbon has maximum catenation, least catenation for lead or no catenation for lead, large size, least bond strength. It is just 81 kilojoules per mole. Okay, so in this video, I have discussed 20 questions. There are many more questions in the P block that can be framed from P block, that is group 13 and 14. So I will be taking those questions in the next video. Okay, so you can just make the notes of these questions till then. Thank you.